Okay, so this is the instruction for 8.2 from the text. It is a calculator, a relatively calculator-dependent assignment. So you're going to want to use a graphing calculator where you can, but if you aren't able to, you can do this by hand, and I'll show you kind of how to do that. So the first thing we want to understand is what do these graphs essentially look like. So we're going to start with a really simple one. It's a graph when x is in the denominator, which is these. Last time we talked about inverse relationships or inverse variations. Well, we're going to graph some of those today in 8.2. So the first one I want to look at with you is question number 4 from your text. And this will give us the structure of how the assignment is kind of going to look. It's y equals 10 over x. And notice x is in the denominator, and so we want to produce a graph of this. We just want to see, what does this graph basically look like? Well, there's two ways to build it. We can make an xy table, okay? And we can pick x values that seem reasonable. And like, if I put 1 in for x, I get 10 for y, because 10 divided by 1 is 10. If I put 2 in for x, I get 5 for y. I don't really want to use 3 or 4, but 5 makes 2. And you can see that as the x's are getting bigger, the y's are getting smaller. The problem is, if you don't know what these graphs look like to start, this is going to be a very slow process. And we might miss some information. So what we want to do is we want to start out, at least initially, with an image in our head of what this looks like as a graph. So I'm going to go to the calculator first, and I'm going to write y equals 10 divided by x. Okay? Now if I go ahead and graph that, something kind of strange happens. It looks a little like an exponential decay function on the right, but on the left, over here, it's a growth function. So we have this graph here, and this graph here, and there's a couple of questions that might be asked, like, well, what happens when it goes down here? And why is it up here over there? What happened? Well, the reality is the graph comes in two pieces. It comes in a left-hand side and a right-hand side. On the left, there's one set of behavior. On the right, there's one set of behavior. Now, if you notice this graph, this equation, it has no pluses or minuses, okay? No pluses or minuses. So when we go to graph this, it means something very special. We have two types of what we call asymptotes or boundaries. So I'm going to talk about the horizontal asymptotes and the vertical asymptotes. Okay? Okay, so in finding the horizontal and vertical asymptotes, there's a couple of rules. Okay? For horizontal asymptotes, we first have to understand that there's an x in the denominator, but there's none in the numerator. Okay? That's important that we understand that. If there's nothing in the numerator, then we look out here and we say, is there a number added or subtracted? It's essentially the k value. You guys remember doing hk? That's essentially what we're going to work with here. That the k value becomes the horizontal asymptote. So there'd be a horizontal asymptote at 0, specifically at y equals 0. And then for the vertical asymptote, we're asking, what makes the denominator 0? This thing that has the x in it, okay, I want to make it 0. What number do you plug in for x? The only thing you can plug in is 0. And so we're going to have a vertical asymptote at x equals 0. Think about making the zeros of the denominator. Okay? So this first one, maybe it'll be a little redundant because there's not a lot of information there. As we go through it, there's going to be a lot more help. So I'm going to draw these dotted lines in. They become my boundaries. Now, we have a horizontal line and a vertical line. There are asymptotes. Okay? And so if I look back at that picture, or I think about these numbers here, I can plot 1, 10, that'll be way up here, and then 2, 5 will be about there, and then 5, 2 will be about there, and I know there'd be 10, 1. So I'm going to have this graph over here that looks basically like this. And you'll notice that it wants to hug the asymptote. It's going to follow right along that boundary on both sides. It likes that boundary, so it goes and stretches to those edges. And then if you look at the graph, you look at the calculator, and we go, let me clear that out. We go to the table, okay? There's an error at 0. That's why we have this boundary line. It's physically impossible to divide 10 by 0. We consider it to be undefined or undoable. So we don't do that. If you look at the list here, I've got -5, -2, -2, -5. So it's sort of the reverse of everything. And so that's why we're going to have this graph down here. Now, as far as points are concerned, I'm not going to get too picky. A point or two would be nice, like -2, -5, probably down here somewhere. But give me a couple of points, but don't get too carried away. This graph is generally speaking what we're looking for. We definitely know where those boundary lines are. And we're going to see another problem where the boundary lines are not at 0, 0. On questions 3 through 10 of your assignment, they're all going to have be centered at 0, or have the horizontal and vertical asymptotes at 0. So let's look at something that is a little bit different, okay? Let's take a quick peek at question number 20. And the next section of the assignment works very much like number 20. 20 is sort of one of the more complicated problems. And so we'll start with that. It also shows us everything. Y equals 10 over x plus 7 and minus 5. Okay? So as we produce this graph, I can go straight to my calculator, and that's fine. But I want to be a little preemptive about it. I want to think about what's supposed to happen here. Okay? I know there's supposed to be a horizontal asymptote and a vertical asymptote. Remember, the horizontal is going to be like k, and the vertical is going to be like h. Okay, from the ordered pair hk that we would find in the first semester. Remember, h was always what made the piece with x 0. So I'm thinking, what would make that denominator 0? Because that's a bad thing. I'm trying to avoid that because I don't know how to divide by 0. So a negative 7 there would work. So here I'm going to say, for my vertical asymptote, x equals negative 7. So I'm going to come down here, 2, 3, 4, 5, 6, 7, and I'm going to draw in that dotted line. Say that's my horizontal asymptote. Or sorry, vertical. Oh, I did that backwards. Let me get that line out here. Okay, and come back this way. Sorry, 2, 3, 4, 5, 6, 7. Let me extend that line. So here at negative 7, I have my horizontal, my vertical. Oh, I cannot speak today. Vertical asymptote, right there at negative 7. And now I need to get my horizontal asymptote. Well, again, you have to make sure that there's no x in the numerator, which there isn't here. So then I look straight over to here, and I see that negative 5 in that position that k always was. So I say y is equal to negative 5. And so I'm going to come down to negative 5, and I'm going to draw my boundary line in here. So now I have 2 new boundary lines, okay? And I want to know, where does my graph show up? Is it here, 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 or here? It'll always be in 2 of those 4 quadrants. I just need to know which one. Now I can test some points, or I can go to the graphing calculator and type it in. It's really important, though, that when you type this stuff in, that you're very clear about how you type it in. So 10 divided by, and you see how I have parentheses there. I'm going to use parentheses around my denominator. It's very important that you do this. Close my parentheses, minus 5, and I'm going to graph that. Now it's hard to see the whole thing, but you can see I'm definitely living on the right. You can imagine that asymptote right through here, and you see this solid line, that is the other asymptote. The newer calculators do a better job of not having that line, but the older calculators are stuck with that. So I just want to mimic this graph onto the page that I have in front of me, and so what I'm going to do, this line's not here. All right, so what I'm going to do is I said it was up in this top right corner, okay, and it's down here in this bottom left corner. And so there's my graph. Now on this section, and starting here and moving forward, it asks me for the domain and the range. And if you struggled with domain and range in the past, this is going to be a really good example of how to do domain and range. Okay, so if you're thinking about domain and range, domain is the x, y. Okay. So as I go, or sorry, it's the x direction. So as I slide along, I'm cruising along my line. Where do I go? Where do I end up with a problem as far as the x is concerned? Should be right here is where I see that first dotted line that says you can't use this x value. And the x value was negative 7. So I'm going to say that x cannot equal negative 7. And if I think about the y values, the range, okay, is up and down. As I'm sliding up, coming up the line, right here I end up with a problem. You run into the boundary and you can't cross there, so you have to jump over the line. But that line exists at negative 5, so y cannot be negative 5. If you look, that'll always be right up here as well. Your domain and range have everything to do with your vertical and horizontal asymptotes. I know there's a lot going on in this problem, but remember, it's about the basic graph. It's about the domain and range, which is built into this equation. So questions number 11 through 22 or 23, they're really built off of the idea of finding h and k. If something's missing, if it seems like there's no k value or there's no h value, that just means it's at 0. Okay. And then the last part of the assignment where there's a big bulk of work to do, because the equations change slightly, is 27 through 34. And there's a slight difference in the way we find our asymptotes because the equations look different. And so we want to be able to have a shortcut so we don't have to do a lot of work. So we're going to look at question number 30. Okay. Y equals 8x plus 3 over 2x minus 6. Okay? And wow, this looks totally complicated in comparison to the other ones. For instance, I don't know what h is, and I don't know what k is. But there's a rule, okay? When there's an x on top and on bottom of the equation, and they have that same, it's just 8x, 2x, and I want to look at just those, okay? For the horizontal asymptote, okay, we're just going to look for what is essentially the slope of the equation when we take just the 8 and the 2. So 8 over 2 equals 4. So then the horizontal asymptote is at y equals 4. So that's a pretty easy thing. You just look at those two values and you just simplify that way. The vertical asymptote is really found the same way. We only focus on the denominator, okay? The vertical asymptote will always come from the denominator because we don't know how to divide by 0. So we need to protect against that. Okay? If you knew where the electric fence was, you'd stay away from it. In the Hunger Games, he's throwing little berries at the force field to try and keep themselves safe. Okay, so we've got to know where that boundary is, and this is how we're going to find it. We're going to say 2x minus 6 equals 0. We're not allowed to be 0 in the denominator, so we're going to figure out what is it we're not supposed to do. So I'll add 6. 2x equals 6, so x equals 3. So my vertical asymptote is that x equals 3. So what that does is when I come over to do my graph, I'm going to come up to 4, 2, 3, 4. I'm going to draw in my horizontal asymptote. Then I'm going to come over to positive 3 and draw in my vertical asymptote. So that creates my 4 spaces that I can draw my curve in. It's just a question of, am I in the top right and bottom left, or the top left and bottom right? Which of the 4 quadrants do I use? Again, we can pick an x and plug it in. And if we know where one of them is, we typically know where the other is. But if you're struggling, let's go ahead and type it in the calculator. I'll erase this real quickly. Alright. So we're going to go y equals, and I'm going to use parentheses a lot here. So 8x plus 3. And notice, other than the 8 from the numerator, I didn't need to know much about the 8x plus 3. Divided by, again parentheses, 2x minus 6. It's very important to use parentheses around the denominator or numerator. And I get this. Again, you see this solid line through the middle? Think of that as the asymptote. And then obviously we said that up at 4 we had our boundary. And you can see that it's in the top right and bottom left. They aren't always that way. If you have some negative numbers involved, sometimes that can alter it, rotate it. Okay, and so there's our graph. We still want to be able to state the domain and range. What's nice about this is the domain and range is really based on the asymptotes. So the domain is about the x's, the range is about the y's. Well, according to my equation, my vertical asymptote was at x equals 3. So I'm going to say x cannot equal 3, and my horizontal asymptote was at y equals 4, so I'm going to say y cannot equal 4. Okay. So this is really useful. We're getting these graphs. They're great. We're finding the domain and range based on those asymptotes. It's pretty straightforward. I do want to take just a second and look at question number 41 with you. It's one of the word problems, and it's very related to the real world and the way that we do things. If you've ever had an ambulance or a police officer drive past you while you're either stopped on the side of the road or while you're inside your house, you'll notice that the sound or the pitch of the sound changes as it goes past you, okay? And I don't want to spend a ton of time on this question, but I want to show you the application that's so important. Okay, so there's a couple of different equations that I want to just look at with you. If you want to know the frequency of the sound, we call it f prime, or in the text they use with a slash after it. We call that the new frequency. I typically would do something more like f prime with an apostrophe after it, equals 740 f s, or the frequency of the sound, divided by 740 plus r. Now the 740 has to do with the speed of sound in air. Okay, how many feet per second it travels. Okay, and we next need the other version. Now this is for when it is moving away from you. Okay, so this is away, and when it's coming towards you, it's f prime equals 740 fs over 740 minus r. And r, of course, is the rate at which the vehicle is traveling. So depending on whether it's coming towards you or away from you, it's going to impact the frequency of the sound you hear. And if you notice, the frequency of the sound, that's predetermined. That's a set value for the siren. It's predetermined. What's different is the rate at which you drive away. And you can see that there's an asymptote here at negative 740 or down here at positive 740. So we see those horizontal and vertical asymptotes exist in a problem like this. It's just very, very cool the way that we can use this inverse variation to solve real problems. So if you want to know how high-pitched a siren can get, you want to know how fast the vehicle is moving, and we can figure that out. One of the reasons we care about that is if you're traveling too fast in the ambulance and your frequency is already really high, you could get up to a really high frequency that would be difficult to hear. So you want to make sure that your frequency stays low enough that everyone can hear it well, but not so low that everyone thinks there's an earthquake or a rumbling sound. They want to be able to clearly tell what it is, no matter what speed the vehicle is traveling within reason. You know, obviously, if the ambulance is going 400 miles an hour, that's a bad thing. Within reason, we want to be able to still hear and understand what's happening when we hear the siren. All right, come to class, prepared to work, and we'll just get her done.